Hello there, and welcome to Nightfall Science. Tonight, we slowly explore black holes, from gravity and event horizons to singularities, time dilation, Hawking radiation, and the strange question of what might truly exist beyond the point where light can no longer return. Let your shoulders relax, and allow these distant ideas to drift gently through your mind. Let's begin. Black holes are often introduced as objects with gravity so strong that nothing can escape. That description is useful, but it also creates several questions immediately. What exactly is a black hole? Is it a hole in space? Is it an object? Is it empty? Does it pull everything toward it like a cosmic vacuum cleaner? And why can light not escape if light has no mass? To understand black holes calmly, we begin somewhere more familiar: gravity. Gravity is the reason objects fall toward Earth. It keeps the moon in orbit. It keeps Earth moving around the sun. It shapes stars, planets, galaxies, and enormous clusters of galaxies. And at the heart of a black hole, gravity has become concentrated into an unusually small region. The story of black holes is therefore not separate from ordinary physics. It begins with the same gravity that keeps your feet on the ground. Imagine holding a ball above the surface of Earth. If you release it, the ball falls. Earth attracts the ball. The ball also attracts Earth, although Earth moves by such a tiny amount that we do not notice. Gravity acts between objects with mass. The larger the mass, the stronger the gravitational attraction tends to be. Distance matters as well. As two objects become farther apart, their gravitational attraction becomes weaker. This relationship was described by Isaac Newton. Newton's law of gravity works extremely well for ordinary situations. It explains planetary orbits. It predicts the motion of moons. It helps spacecraft travel through the solar system. And it gives us our first gentle step toward understanding black holes. Imagine standing on Earth and throwing a ball upward. If you throw slowly, the ball rises for a moment. Then gravity brings it back. Throw it faster, and it rises higher before returning. Throw it faster still, and it travels even farther. There is a certain speed at which the ball would no longer return to Earth. It would escape Earth's gravitational influence and continue outward. This is called escape velocity. If the sun were somehow compressed without changing its mass, it would need to become only a few kilometers across before a black hole formed. The total mass could remain identical. The difference would be concentration. This leads to a subtle point. A black hole does not necessarily have more gravitational pull from far away than another object with the same mass. Suppose the sun were magically replaced by a black hole with exactly one solar mass. Earth would not suddenly fall inward. Ignoring the impossible process that created it, Earth could continue orbiting almost as before. From our distance, the gravitational effect would be determined primarily by the central mass. One solar mass is still one solar mass. The dramatic behavior appears when we move extremely close to the black hole. There, space-time becomes strongly curved. This is where Newton's description becomes incomplete. Albert Einstein gives us a deeper picture. In general relativity, gravity is not treated simply as an invisible force pulling objects through space. Mass and energy affect the geometry of space-time itself. Space-time is the combined structure of space and time. In Einstein's theory, the sun changes the geometry of space-time around it. Earth follows a path through that geometry. What we describe as Earth orbiting because of gravity can also be described as Earth moving along the natural curved path available within the sun's distorted space-time. The stronger the gravitational environment, the stronger this curvature becomes. Near a black hole, the curvature can become extreme. Space and time behave in ways that seem unusual from everyday experience. Clocks can run at different rates, paths of light can bend dramatically, and beyond a particular boundary, every possible future-directed path points deeper inward. That boundary is called the event horizon. Gas may become extremely hot as it falls inward. Light from background objects may bend. Matter can form a glowing accretion disk. Gravitational waves can be produced when black holes collide. So invisible does not mean undetectable. We often learn about unseen things through their effects. The event horizon of a non-rotating black hole has a characteristic size called the Schwarzschild radius. This radius depends upon the black hole's mass. More mass means a larger horizon. A black hole with the mass of the sun would have a Schwarzschild radius of roughly 3 kilometers. The singularity is a very different concept. In the simplest classical description of a non-rotating black hole, matter collapsing inward continues until the equations predict a region where curvature becomes infinite and ordinary descriptions break down. This is called a singularity. It does not necessarily mean that physicists believe nature literally contains an infinitely dense mathematical point in the simplest possible sense. A singularity often tells us that the theory being used has reached the edge of its applicability. General relativity describes gravity extremely well. Quantum mechanics describes microscopic physics extremely well. But inside the deepest region of a black hole, we expect both gravity and quantum effects to become important. We do not yet have a complete experimentally confirmed theory of quantum gravity that unifies them. So the singularity marks one of the places where our current theories stop providing a complete picture. From far away, gravity might feel similar to that of any object with the same mass. As you move closer, differences become stronger. Light traveling near the black hole follows curved paths. A distant observer watching you fall would see your light increasingly redshifted. Redshift means the light stretches toward longer wavelengths. Your signals would also arrive more slowly from the distant observer's perspective. This can create the impression that you are slowing down as you approach the horizon. In the idealized mathematical description, the outside observer never receives a signal showing you crossing the event horizon. Instead, your light becomes increasingly faint and redshifted. Eventually, it becomes effectively impossible to detect. From your own perspective, however, the experience is different. Your own clock continues normally. If the black hole is large enough and the environment is calm enough, you could cross the event horizon in a finite amount of your own time. You would not necessarily encounter a solid surface. There might not be a bright line marking the boundary. Locally, especially around a very large black hole, crossing the event horizon could be uneventful. This apparent disagreement is one of the famous puzzles of black hole descriptions. How can a distant observer say you appear to freeze near the horizon while you say you cross it? The answer comes from relativity. Different observers can use different coordinates and experience different relationships between time and space. The photon sphere plays an important role in the appearance of a black hole. When telescopes create images associated with black holes, the dark central region is not simply a photograph of the event horizon itself. The image is shaped by curved light paths, glowing material, and the black hole's shadow. The shadow is generally larger than the event horizon. Light from behind the black hole can bend around it. Some rays reach the observer, others are captured. The resulting image contains a dark region surrounded by bright distorted emission. The famous bright ring often comes from hot plasma around the black hole and gravitational lensing. The horizon itself remains dark. Matter falling toward a central supermassive black hole releases enormous amounts of energy before crossing the horizon. A quasar can outshine the rest of its host galaxy. The energy does not come from matter mysteriously glowing inside the black hole. It is released outside the horizon as material falls deeper into the gravitational field and interacts within the accretion flow. Accretion can convert mass into radiation with remarkable efficiency. Black holes can therefore appear associated with extremely bright environments. Black does not mean the surrounding region is dark. It means light cannot escape from inside the horizon. Some black holes also produce powerful jets. These jets can extend far beyond the galaxy. They consist of energetic particles moving along directions associated with magnetic fields near the rotating accretion system. The black hole does not simply spray matter outward from inside the horizon. Material that has already crossed the event horizon cannot return in the ordinary picture. Instead, jets are launched from regions outside the horizon through interactions involving magnetic fields, rotating plasma, and the black hole's spin. Rotation introduces another layer. Real astrophysical black holes are expected to rotate. A rotating black hole is described differently from an ideal non-rotating one. The simplest rotating solution in general relativity is called a Kerr black hole. Rotation changes the structure of spacetime around it. The black hole effectively drags nearby spacetime around with its rotation. This effect is called frame dragging. Near a rotating black hole, remaining perfectly stationary relative to distant space can become impossible. There is a region outside the event horizon called the ergosphere. Inside the ergosphere, objects are forced to move in the direction of the black hole's rotation relative to distant observers. They can still escape from the ergosphere. So the ergosphere is not the same as the event horizon. The horizon remains the deeper boundary from which escape becomes impossible. The ergosphere is especially interesting because, in principle, energy can be extracted from a rotating black hole. A process known as the Penrose process describes how this can occur theoretically. Magnetic processes in realistic astrophysical environments can also tap rotational energy and contribute to powerful jets. Quantum mechanics strongly suggests that fundamental information should not simply be destroyed, but classical black hole descriptions seem to hide it permanently. The tension between these ideas leads to the black hole information paradox. We will explore that slowly in a later part. For now, It is enough to notice that a black hole creates a boundary between what is accessible from outside and what is not. The event horizon is therefore not merely a region of strong gravity. It is a boundary of information. This is one of the deepest ways to think about it. Imagine shining a flashlight outward while falling toward a black hole. Far outside, some of the light escapes. A gravitational gradient means the strength of gravity changes across a distance. Tidal effects exist everywhere. The moon creates tides on Earth because the side of Earth closer to the moon experiences a slightly different gravitational effect from the far side. Near a black hole, these differences can become enormous, but the strength of tidal forces at the event horizon depends strongly on the black hole's mass. For a small stellar mass black hole, tidal forces near the horizon can be extremely strong. For a supermassive black hole, the horizon can be so large that the gravitational gradient across a human-sized body at the horizon may be relatively gentle. You could cross the horizon before experiencing the strongest tidal effects. This can feel counterintuitive. A larger black hole sounds as though it should be more dangerous at its horizon. A freely falling observer may feel locally weightless while falling inward. The danger comes from differences in gravity across the body and from whatever matter or radiation exists nearby. This is an application of Einstein's equivalence principle. Locally, free fall can resemble floating in gravity-free space. Imagine standing inside an elevator whose cable has been cut in a purely ideal thought experiment. Everything inside falls together. Objects appear to float relative to one another. Einstein used ideas like this to connect acceleration and gravity. Near a black hole, free fall remains locally natural. The global space-time structure is what makes the event horizon so unusual. Local physics can feel ordinary even while the larger geometry ensures there is no route back out. This difference between local and global descriptions appears repeatedly in relativity. You may cross a horizon without encountering a physical wall locally, yet globally, you have entered a region that cannot communicate with infinity. Both statements can be true. Black hole physics often feels confusing because our everyday intuition expects space and time to behave separately and absolutely, but relativity asks us to treat them as parts of one geometry. A horizon is easier to understand when viewed as a feature of space-time, rather than a dark spherical object floating inside ordinary space. The black hole is not simply sitting in space like a bowling ball. The black hole is a region where space-time geometry has taken a particular form. Gravity is not instantaneous. Changes in the gravitational field propagate at the speed of light. When massive objects accelerate asymmetrically, they can generate gravitational radiation. Black hole mergers are especially strong sources because enormous masses move at significant fractions of the speed of light within extremely curved spacetime. After two black holes merge, the final object can vibrate briefly. These vibrations are called quasi-normal modes. They fade as energy leaves through gravitational waves. Quantum physics changes the story. For now, remain with the simplest picture. A black hole forms when enough mass or energy is concentrated strongly enough that spacetime develops an event horizon. The event horizon is not a solid surface. It is a causal boundary. Light inside cannot escape. A distant observer sees signals from approaching objects become increasingly delayed and redshifted. A falling observer can cross a sufficiently large horizon in finite proper time. Gravity near a black hole is described most accurately as curved spacetime. Light responds because it follows that geometry. A black hole is what happens when that geometry becomes extreme enough to create a horizon. There is no need to picture a tunnel, no need to imagine a giant cosmic drain, and no need to think of a black hole as a mysterious object ignoring the rest of physics. It is one of the clearest places where the rules of relativity become impossible to ignore. The rules remain consistent. Our everyday intuition simply comes from a much gentler gravitational environment. Here on Earth, space-time curvature is weak enough that Newton's description works beautifully for most ordinary situations. Clocks around us run at nearly the same rates. Light travels along paths that appear almost straight. Mass curves space-time. More compact mass creates stronger curvature. Push this concentration far enough, and an event horizon forms. That is where our journey begins. In the next part, we will move more deeply into how black holes actually form, why some dying stars become neutron stars while others collapse farther, what stellar mass and supermassive black holes are, how scientists find objects that emit almost no light of their own, and how black holes can quietly grow across billions of years. Black holes do not appear from nowhere. They have histories. They form from matter. They grow. They interact with stars and gas. And in many cases, they begin with something that seems almost opposite to a black hole, a shining star. To understand how a black hole can emerge from a star, it helps to begin with the quiet balance that keeps a star alive. A star is held together by gravity. Every part of the star attracts every other part. The enormous mass pulls inward toward the center. If gravity acted alone, the star would collapse. But gravity is not acting alone. Deep inside the star, temperatures and pressures are extremely high. Atomic nuclei move rapidly. They collide, and under the right conditions they fuse. Fusion releases energy. That energy helps support the star against gravitational collapse. The star exists in a long-lasting competition. Gravity pulls inward. Internal pressure pushes outward. For much of a star's life, these effects remain close to balance. This condition is called hydrostatic equilibrium. The word sounds technical. The idea is simple. Each layer of the star is supported by pressure from below, while gravity pulls it inward. The star does not need to be perfectly motionless. Real stars vibrate, rotate, flare, and change. But over long periods, the overall structure can remain remarkably stable. Our Sun has spent billions of years in this state. In its core, hydrogen nuclei fuse into helium. The process releases energy. That energy slowly works its way outward. Eventually, some of it reaches space as sunlight. The same light that warms Earth began with nuclear reactions deep inside the Sun. A massive star follows the same basic principle. If the collapsed core is too massive to be supported as a neutron star, continued collapse can produce a black hole. A neutron star is already an extraordinary object. It contains roughly stellar amounts of mass in a sphere only tens of kilometers across. Its matter is compressed far beyond ordinary atomic density. A small amount of neutron star material, if somehow removed and kept stable, would have an enormous mass by everyday standards. The star is supported by quantum effects and nuclear interactions. But this support has limits. There is a maximum mass beyond which a stable neutron star cannot exist under standard physics. The exact maximum depends on the uncertain equation of state of ultra-dense matter. The phrase equation of state describes how pressure, density, temperature, and other properties are related. The exact formation of an event horizon is best understood globally. To know with certainty whether an event is inside the event horizon, one must consider whether light from that event can ever reach the distant future. This is one reason horizons are subtle. They are not simply determined by measuring a local field strength at one instant. They are features of the larger space-time. Now consider the explosion surrounding the collapse. Many massive stars end their lives in supernovae. A supernova can temporarily shine with the brightness of an entire galaxy. Material from the star is expelled into space. Nature has more than one route from a massive star to a black hole. Binary systems create even more possibilities. A binary system contains two stars orbiting one another. Many stars in the galaxy belong to multiple star systems. If one star becomes a black hole while the companion survives, the black hole can remain gravitationally bound to that companion. This creates one of the most useful ways to detect stellar mass black holes. The black hole itself may be dark, but the companion star moves. Its motion can reveal the invisible mass. Imagine watching a visible star orbit an apparently empty point. Or suppose the black hole and companion orbit closely enough that the black hole's gravity pulls material from the star. The gas does not usually fall directly inward. It has angular momentum. Angular momentum is the rotational counterpart of ordinary momentum. Because the gas is moving sideways as well as inward, it tends to orbit. The material forms an accretion disk. Inside the disk, neighboring regions move at different orbital speeds. Magnetic fields and turbulence help transfer angular momentum outward. Some material loses enough angular momentum to move closer to the black hole. As it falls deeper into the gravitational field, gravitational potential energy is converted into other forms. Most simply orbit through the galaxy under the same broad gravitational rules as stars. Space is extremely large. The chances of a random isolated black hole passing close to Earth are very small. A black hole several light years away would not create a special threat simply because it is a black hole. Its distant gravity would behave like the gravity of any other object with the same mass. To cause dramatic effects, it would need to pass relatively close. The idea of invisible black holes moving through the galaxy may sound strange, but astronomy has always involved detecting unseen objects indirectly. Darkness does not remove gravity. One possible way to find an isolated black hole is gravitational microlensing. Gravitational lensing occurs because mass bends spacetime, and therefore the paths of light. Suppose a black hole passes almost directly between Earth and a distant background star. The black hole's gravity bends light from that star. the background star may appear temporarily brighter. Its apparent position may shift slightly. The black hole acts as a gravitational lens. Because the alignment changes as the objects move, the effect evolves with time. By measuring the brightness change and the positional shift carefully, astronomers can estimate properties of the lensing object. If the invisible lens has a sufficiently large mass, a black hole may be indicated. One possibility begins with the first generations of massive stars. The early universe contained mostly hydrogen and helium, with very few heavier elements. Some early stars may have grown to unusually large masses. Their collapse could have produced relatively heavy stellar black hole seeds. Those seeds could then grow. Another possibility is direct collapse. Under particular conditions, a large gas cloud might collapse into a massive black hole seed without first forming an ordinary long-lived star. This could produce seeds thousands, or perhaps tens of thousands of times the sun's mass. A larger starting point makes later growth easier. Dense star clusters may offer other routes. Only a small amount of material is accreting. The black hole still strongly influences stars in the innermost region through gravity. Some stars orbit it extremely rapidly. By tracking these stellar orbits over years, astronomers can map the gravitational field. One particular class of stars near the galactic center completes very elongated orbits around the central invisible mass. At their closest approaches, their speeds can become enormous. The measured paths fit the presence of a compact object containing millions of solar masses. The central mass is confined to such a small region that a supermassive black hole is overwhelmingly the best explanation. These stellar orbits also allow tests of relativity. Others bend around the black hole. The combination produces a dark central shadow surrounded by bright emission. Creating such an image requires extraordinary resolution. The black holes are extremely distant. Their apparent size in our sky is tiny. To achieve the necessary resolution, astronomers use very long baseline interferometry. Radio telescopes spread across Earth observe together. Their data are combined in a way that effectively creates a telescope with a size comparable to the distance between observatories. This is the basic idea behind the Event Horizon Telescope. By synchronizing observations across the planet, astronomers can resolve scales near the event horizons of supermassive black holes. The first widely publicized black hole image showed the central object in the galaxy M80. Later observations produced an image associated with Sagittarius A star. The glowing rings are not photographs of a hard surface. They are maps of radio emission shaped by relativistic gravity. The dark interior is associated with the black hole's shadow. This distinction matters because the shadow is larger than the event horizon. Light can be captured even when it does not cross the horizon immediately. The strongly curved photon trajectories create a region from which little radiation reaches the observer. When simulations based on general relativity and plasma physics are compared with observations, the broad agreement is striking. Black hole theory predicts the size and shape expected from the measured mass. Accretion does not add all incoming mass directly to the black hole. Some of the mass energy can be radiated away before crossing the horizon. The efficiency depends on the accretion flow and the black hole's spin. For a rotating black hole, material can orbit stably closer to the horizon in some directions. More gravitational binding energy may be released before the matter falls in. This can make accretion remarkably efficient compared with ordinary nuclear fusion. A significant fraction of the rest mass energy of infalling matter can emerge as radiation. This is why quasars can be so luminous. A relatively small central region can produce immense power. A larger black hole forms. The final mass is slightly less than the simple sum of the two initial masses, because some mass energy is carried away by gravitational waves. This is a direct demonstration of mass energy equivalence. Energy leaving the system reduces the mass of the final object compared with the sum of what went in. The emitted gravitational wave energy can be enormous. For a brief moment, the power carried by gravitational waves from a major black hole merger can exceed the electromagnetic luminosity of vast numbers of stars. Yet the waves interact so weakly with matter that by the time they reach Earth, they create unbelievably tiny distortions. Detectors must measure changes far smaller than an atomic nucleus across kilometer-scale instruments. This contrast is remarkable. The source is extraordinarily energetic. The signal at Earth is extraordinarily subtle. The first direct detection of gravitational waves from a binary black hole merger transformed black hole astronomy. Before that, stellar mass black holes were mainly studied through electromagnetic effects and binary dynamics. Gravitational waves gave astronomers access to black hole systems that might emit almost no light. Two isolated black holes can merge in darkness. No bright accretion disk is required. Space-time itself carries the signal. This revealed populations of black holes with masses and combinations that expanded our understanding of stellar evolution. It also opened the possibility of studying black holes across the universe through repeated detections. Each merger is like a short message containing information about the objects. Some black holes can merge repeatedly. A black hole formed from one merger may later merge with another. This hierarchical growth could produce unusually massive stellar origin black holes. It may help populate mass ranges that are difficult to reach through ordinary single-star evolution. The phrase stellar mass black hole therefore does not always mean the object came directly from one star and never changed. It describes a broad mass scale. The object's history may involve accretion or mergers. Intermediate mass black holes occupy a rough range between stellar and supermassive objects. They are especially interesting because evidence for them has historically been more difficult to establish. An intermediate mass black hole might contain hundreds, thousands, or perhaps tens of thousands of solar masses. Stellar mass black holes in binaries can change their X-ray brightness quickly. Supermassive black hole accretion disks evolve on longer characteristic scales, yet quasars can still vary enough to reveal that their enormous luminosity comes from a compact region. If an object changes brightness significantly over a short period, the emitting region cannot be arbitrarily large. Why? Because information about the change cannot travel faster than light. A region one light day across cannot coordinate a complete brightness change much faster than about a day through ordinary causal processes. Rapid variability therefore places an upper limit on the size of the emitting region. This reasoning helped astronomers realize that quasars must be incredibly compact despite their enormous luminosities. A whole galaxy cannot normally brighten and dim in perfect coordination over such short times. The power source must be concentrated. A supermassive black hole with an accretion disk provides that compact engine. Black holes can also consume stars. Near a supermassive black hole, a star passing too close may experience tidal forces strong enough to tear it apart. This is called a tidal disruption event. The side of the star closer to the black hole feels a stronger gravitational pull than the far side. If the difference becomes larger than the star's self-gravity can withstand, the star is disrupted. Some of the stellar debris may escape, some remains bound. If the same mass were compressed into a black hole, the exterior orbit at Earth's distance would barely care about the compression. Only much closer would the relativistic differences become dramatic. This illustrates a general principle in gravity. Outside a spherically symmetric mass distribution, the gravitational field can behave as though the mass were concentrated at the center. Black holes take this compactness to an extreme. They do not create unlimited gravitational attraction at every distance. Their special nature becomes important near the horizon. This also explains why the central supermassive black hole does not dominate the entire Milky Way. Sagittarius, a star, contains millions of solar masses. That sounds enormous, but the galaxy contains hundreds of billions of stars along with gas and dark matter. Far from the central region, the gravitational contribution from the black hole becomes only one part of the galaxy's total mass distribution. Our solar system does not orbit Sagittarius, a star, in the same simple sense that Earth orbits the Sun. The Sun and nearby stars move through the combined gravitational potential of the entire galaxy. The central black hole dominates, only relatively close to the galactic center. Scale determines influence. Another confusion comes from black holes and density. We often say a black hole forms when matter becomes extremely dense. That is useful for stellar black holes. The interior geometry is not a simple static sphere of matter. The average density calculation is only a mathematical comparison, but it shows why statements like black holes are infinitely dense everywhere are misleading. The event horizon is not a region filled uniformly with infinite density matter. Classical relativity places the singular behavior deeper inside. The horizon itself can exist in a region with finite local curvature, especially for a supermassive black hole. This distinction helps remove some of the mystery. A black hole is defined by its horizon and causal structure, not by every point inside having some unimaginably large density. The phrase collapsed object can also mislead us into imagining a permanent lump of matter sitting at the center. According to classical general relativity, the interior is dynamic in an unusual sense. Inside a simple black hole, moving toward the central singularity is in some ways as unavoidable as moving toward the future. The radial coordinate takes on a time-like character. This is difficult to visualize because our everyday experience separates space and time. Outside the horizon, we can choose to move inward or outward. Inside, the future structure prevents turning around and returning through the horizon. This is not because a force is pulling a stationary object through ordinary space. It is because the allowed future directions of space-time all lead inward. The details of realistic interiors are more complicated. Infalling observers cross in finite proper time. Other coordinate systems describe the horizon smoothly. Astronomically, the object behaves as a black hole. There is no practical distinction where we must wait an infinite time before black hole physics begins. Coordinate time is not universal physical time. Relativity asks us to distinguish mathematical coordinates from measurable local experiences. This lesson appears again and again. An inconvenient coordinate can make a horizon look singular, even where physical curvature is finite. Changing coordinates can remove that artificial singularity. The central singularity, by contrast, cannot be removed so simply in classical relativity. Before reaching it, there is more to understand about the horizon itself. Because black holes do not merely form and sit quietly, matter approaching the horizon can create some of the most extreme environments in the universe. Magnetic fields can become organized on enormous scales. Plasma can orbit at relativistic speeds. Radiation can be strongly redshifted. The black hole can spin fast enough to drag nearby spacetime significantly. Energy can be extracted from the rotational system or remain nearly invisible. It may orbit another compact object, drift through a galaxy, sit at the center of a star cluster, or anchor the innermost region of a giant galaxy. The horizon itself remains dark, but the universe around it can tell us the black hole's story, and that story is still unfolding. In the next part, we will move closer to the edge itself and explore what matter experiences near an event horizon, why accretion disks become so hot, how black hole spin changes the surrounding spacetime, what the photon sphere and innermost stable orbit really mean, how relativistic jets may form, and why an object that emits no ordinary light can power some of the brightest structures in the cosmos. A black hole itself is dark, yet the region around a black hole can become one of the brightest places in the universe. This sounds contradictory at first. If nothing can escape from inside the event horizon, how can a black hole be associated with intense radiation? The answer is that most of the light does not come from inside the black hole. It comes from matter that is still outside. Gas, dust, plasma, and sometimes the remains of disrupted stars. This material can orbit the black hole for a long time before finally crossing the horizon. As it moves inward, it can release enormous amounts of energy. To understand why, begin with an ordinary orbit. Earth moves around the sun. The planet is constantly falling toward the sun because of gravity, but it also moves sideways quickly enough that it keeps missing the sun. The result is an orbit. Matter around a black hole can behave in the same basic way. A cloud of gas approaching the black hole rarely falls perfectly straight inward. It already has some sideways motion. This means it carries angular momentum. Angular momentum makes direct collapse difficult. The gas begins orbiting. As more material arrives, it forms a rotating structure. This structure is called an accretion disk. The word accretion simply means growth through the gradual accumulation of matter. The black hole grows because matter moves through the disk and eventually crosses the horizon. But the disk is not like a solid plate. It is made of plasma and gas. Different regions orbit at different speeds. Closer material must move faster. Farther material moves more slowly. This difference creates shear. Neighboring layers slide past one another. Magnetic fields become twisted. Turbulence develops. These interactions allow angular momentum to move outward. This is essential. Without losing angular momentum, matter could remain in orbit instead of falling inward. Imagine trying to move closer to the center of a spinning carousel while preserving the same angular momentum. X-rays, visible light, and other wavelengths depending on the black hole's mass and accretion rate. The glowing disk can therefore be much easier to see than the black hole itself. The black hole remains the dark center. The accretion flow reveals where it is. An important idea here is efficiency. When matter falls toward an ordinary star, some gravitational energy is released. When matter falls deep into the gravitational field of a black hole, much more can be released before the matter crosses the horizon. In some black hole accretion systems, a significant fraction of the matter's rest mass energy can emerge as radiation. Inside this radius, circular orbits become unstable. Matter can no longer remain peacefully in a stable circular path. A small disturbance can send it plunging inward. The exact location of the ISCO depends strongly on the black hole's spin. For a non-rotating black hole, the ISCO lies outside the event horizon at a radius 3 times the Schwarzschild radius. For a rotating black hole, the situation becomes more interesting. If the disk orbits in the same direction as the black hole's spin, stable circular orbits can exist closer to the horizon. If the disk moves in the opposite direction, the ISCO lies farther away. This means spin affects accretion efficiency. A rapidly rotating black hole can allow matter orbiting in the same direction to spiral deeper into the gravitational field before plunging inward. The phrase is only a picture. Mathematically, the geometry of spacetime includes rotational effects. Paths that would otherwise be equivalent become different depending on whether they move with or against the spin. The closer we move to the black hole, the stronger this distinction becomes. Outside the horizon of a rotating black hole lies the ergosphere. The ergosphere has an unusual property. Inside it, no object can remain completely stationary relative to distant observers. Spacetime is dragged so strongly that every future directed path must rotate in the same general direction as the black hole. An object can still move around locally. It can still escape from the ergosphere. The other escapes with more energy than the original particle carried in from infinity. The extra energy comes from the black hole's spin. This is the Penrose process. It is difficult to realize efficiently through simple particle splitting in nature, but it shows that a rotating black hole contains extractable rotational energy. Astrophysical magnetic fields may provide a more realistic route. Near a rotating black hole, magnetic field lines threading the surrounding plasma can interact with the rotating spacetime. Energy can be carried outward. This is related to models of powerful relativistic jets. Jets are among the most dramatic structures associated with black holes. The central engine may be roughly solar system sized. The resulting structures may extend farther than the visible galaxy. This enormous contrast in scale is one reason active black holes are so important in cosmology. Black holes are small compared with galaxies, but active black holes can regulate galaxies. Now consider what the accretion disk actually looks like. Popular illustrations often show a flat, glowing ring with a dark center. From a distant viewing angle, relativity changes that appearance. Light from the backside of the disk can bend over and under the black hole. Near the event horizon, all of these effects become significant at once. The region can therefore look very different from ordinary intuition. Light emitted close to the black hole loses energy as it climbs outward through the gravitational field. A distant observer sees the light gravitationally redshifted. The wavelength becomes longer. The closer the emission occurs to the horizon, the stronger this effect can become. At the same time, matter in the disk may be moving toward or away from the observer at relativistic speeds. Doppler shifts can move the light in the opposite direction. The final observed spectrum contains a mixture of effects. Astronomers can study these distorted spectral features to infer conditions near the black hole. One particularly useful example comes from iron. Hot accretion disks can produce X-ray emission lines associated with iron atoms. In a laboratory, such a line would have a relatively well-defined energy. Near a black hole, the line becomes broadened and distorted. Some of the light is redshifted by gravity, some is Doppler shifted by orbital motion, some is strongly boosted from the approaching side. The resulting shape can provide information about how close the disk extends to the black hole. And because the ISCO depends on spin, these observations can help estimate black hole spin. The black hole itself remains unseen. Its rotation is inferred from the behavior of surrounding light. This is a recurring theme. Black holes reveal their properties through effects: mass through orbits, spin through accretion geometry and gravitational waves, presence through lensing, mergers through spacetime vibrations. We learn about the dark object by watching the universe respond to it. Now move slightly away from the disk and consider the photon sphere. A photon sphere is a region where light can orbit a non-rotating black hole along unstable circular trajectories. The closer a ray comes to the critical orbit, the more it can wind around the black hole before leaving. In principle, this creates an infinite sequence of increasingly thin photon rings. In practice, resolving these structures is extremely difficult, but they are an important theoretical feature of black hole imaging. The black hole shadow emerges from this behavior. Imagine a glowing background behind the black hole. Some light rays bend around and reach us. Others pass too close and are captured. The observer sees a dark region corresponding to directions from which light does not arrive. This region is the shadow. The phrase refers to what the distant observer receives. In practical astronomy, the object fades too much to remain visible. You do not continue watching it as a bright stationary figure for eternity. The signal disappears. From the falling object's own perspective, it crosses the horizon. These two descriptions are not contradictory once we remember that relativity does not provide one universal time. The coordinates used by the distant observer behave badly at the horizon. Other coordinate systems describe the crossing smoothly. The size of the black hole matters. For a stellar mass black hole, the time between horizon crossing and the classical singularity can be extremely short. For a supermassive black hole, it can be much longer, but the singularity is still in the future of the infalling observer. There is no path that remains forever at a fixed radius. No orbit below the horizon can stay stable. No rocket can hover. The interior is not simply an ordinary region of space from which escape happens to require too much speed. The causal structure is different. This is why many science fiction pictures of living inside a black hole are difficult to reconcile with simple classical models. Quantum effects may also change the deep interior, so the beautiful mathematical extensions of an eternal ideal Kerr black hole should not automatically be interpreted as realistic tunnels through nature. This is an important distinction between mathematical possibilities and physical expectations. Einstein's equations can have strange exact solutions. Whether nature actually creates stable versions of those solutions is another question. A wormhole is a hypothetical shortcut connecting distant regions of space-time. Some mathematical solutions resemble wormholes. The original Einstein-Rosen bridge connects regions in an idealized black hole geometry, but it is not traversable in the simple form. It closes too quickly for ordinary matter to pass through from one exterior region to another. Traversable wormholes require additional ingredients, often including forms of exotic matter with unusual energy properties. There is no observational evidence that astrophysical black holes are entrances to traversable wormholes. So when popular culture shows a spacecraft entering a black hole and emerging somewhere else, it is moving beyond established black hole physics. The idea is fascinating. The evidence is not there. Black holes are already strange enough without turning them automatically into portals. The same caution applies to white holes. A white hole is, roughly speaking, the time-reversed mathematical counterpart of a black hole. Nothing can enter a white hole from the outside. Matter and radiation can emerge. Imagine a very massive black hole with little surrounding gas. This removes the dangerous radiation of an active accretion disk. You fall toward it in a spacecraft. Far away, your engines may allow complicated maneuvers. Closer in, stable circular orbits disappear. Once you pass the ISCO, you cannot simply settle into another stable circular orbit. You can still fire engines and alter your trajectory for a while, but the set of possible paths becomes increasingly restricted. Eventually, the horizon is crossed. Locally, nothing necessarily announces the exact instant. For a supermassive black hole, the horizon can be crossed before severe tidal disruption. This difference does not mean the supermassive black hole has weaker overall gravity. It means the gravitational gradient at its much larger horizon is smaller across a human-sized distance. Gravity and tidal gravity are not identical ideas. Weight depends on acceleration relative to a support. Tides depend on differences in acceleration between nearby points. Near Earth's surface, the gravitational acceleration is about the same across a person's height, so tidal effects are tiny. Near a small black hole, the change can be enormous. The distinction helps explain another strange fact. Astronomers describe this using accretion rate, how much matter reaches the inner accretion flow per unit time. A high accretion rate can produce a luminous thin disk. At much lower rates, the flow may become hot and diffuse. Radiatively inefficient accretion flows can carry much of their energy inward rather than radiating it efficiently. Different accretion states produce different spectra. Black hole binary systems can even transition between states. Their X-ray emission changes. Jets may become stronger or weaker. The disk geometry evolves. The answer again lies in global spacetime rather than a simple visual sequence. The gravitational field evolves. The black hole's mass includes energy associated with the infalling matter. The horizon can grow. From an exterior viewpoint, the spacetime responds consistently. The fading optical appearance does not prevent the black hole from absorbing energy. The statement "never see it cross" should not be confused with "never becomes part of the black hole." The observer simply does not receive a signal showing the local crossing event. This distinction matters. What we observe through light is not the same as the full geometry of the event. The final black hole is larger. Its horizon area has increased. This leads to one of the most profound discoveries in black hole physics. Classically, the total area of black hole event horizons cannot decrease under suitable conditions. This is known as Hawking's area theorem. The horizon area behaves strangely like entropy. In thermodynamics, entropy tends to increase. In black hole physics, horizon area also tends to increase classically. This similarity was initially thought to be only an analogy. Temperature usually suggests thermal motion. Hot objects radiate. A classical black hole does neither in the ordinary sense. Yet the mathematical laws governing black holes resemble the laws of thermodynamics. Surface gravity plays a role similar to temperature. Horizon area plays a role similar to entropy. Mass plays a role similar to energy. These parallels are too precise to ignore. Quantum field theory in curved spacetime transforms the analogy into physical thermodynamics. The black hole is not perfectly black after all. A single horizon links several major areas of physics. This is why black holes are so useful intellectually. They force our theories to meet. General relativity says spacetime curves. Quantum theory says fields fluctuate and information evolves according to quantum rules. Thermodynamics says entropy and temperature govern large collections of microscopic possibilities. At a black hole horizon, all three ideas become difficult to separate. The black hole becomes more than an astronomical object. It becomes a test of whether our deepest laws can fit together. Before moving toward those quantum puzzles, gather the geometry around the black hole once more. The shadow can therefore appear larger than the horizon. The accretion ring seen around it is also not the photon sphere itself. It is emission from hot plasma distorted by strong lensing. Different pieces of the image correspond to different physical effects. Once separated, the picture becomes much clearer. The glowing part is matter outside. The dark part is a lensing and capture effect. The horizon lies inside the apparent shadow. The photon trajectories wrap around the spacetime, and the observer receives only the rays that survive. Nothing magical needs to be added. The strange appearance comes from gravity becoming strong enough that the geometry of spacetime can no longer be ignored. And this geometry raises the next question. If black holes absorb matter and radiation, and if nothing classically returns, what happens to all the energy and information that crosses the horizon? Does it remain hidden forever? Can a black hole last forever, or can it slowly disappear? In the next part, we will move gently into black hole thermodynamics, entropy, temperature, Hawking radiation, why black holes can gradually evaporate, why smaller black holes are hotter than larger ones, and how the simple question of whether information can truly disappear becomes one of the deepest puzzles in modern physics. A black hole seems like the last place we would expect to find temperature. Temperature usually belongs to warm gas, hot metal, stars, fire, or countless particles moving and colliding. A black hole, by contrast, appears almost perfectly dark. Classically, nothing comes back from inside the event horizon. Matter can fall in, light can fall in, energy can fall in. But once inside, the outside universe cannot recover them through ordinary motion. So for a long time, the idea that a black hole could have a temperature sounded strange, and yet black holes behave in ways that closely resemble thermodynamic systems. Thermodynamics is the branch of physics that studies heat, energy, temperature, and entropy. Entropy is one of the more confusing ideas in physics. It is often described as disorder. That description can be useful in some situations, but it is incomplete. A more careful way to think about entropy is as a measure of how many microscopic arrangements can produce the same overall macroscopic state. Imagine a box containing gas. From far away, we may know the temperature, the pressure, the volume, and the total number of molecules. Those are macroscopic properties. But inside the box, every molecule has a particular position and velocity. There are an enormous number of possible microscopic arrangements consistent with the same temperature and pressure. Entropy is connected to the number of those hidden possibilities. the more microscopic states correspond to the same overall appearance, the larger the entropy. This perspective becomes important for black holes, because a black hole looks astonishingly simple from the outside. Mass, spin, charge. Those are almost all the classical properties we can use to describe a stationary black hole. But the matter that formed it may have been extraordinarily complicated. Perhaps thousands of stars collapsed and merged. Perhaps gas containing countless different atoms fell inward. Perhaps planets, dust. The exact Bekenstein-Hawking entropy is proportional to the horizon area divided by a tiny fundamental unit known as the Planck area. The Planck area is unimaginably small, so even a modest astrophysical black hole has an enormous entropy. A black hole may contain more entropy than ordinary matter, with the same energy packed into the same region. This suggests that black holes are not simple in the microscopic sense. They only look simple from the outside. Behind the few macroscopic parameters may lie an immense number of hidden microscopic states. What those states physically are remains connected to quantum gravity. Double the mass, the temperature becomes roughly half as large. A supermassive black hole is therefore extremely cold. A stellar mass black hole is also extremely cold by everyday standards. The Hawking temperature of an astrophysical black hole can be far below the temperature of the cosmic microwave background. The universe itself bathes black holes in background radiation. If the incoming radiation is greater than the black hole's Hawking emission, the black hole gains more energy than it loses. So present-day astrophysical black holes do not generally evaporate rapidly. They absorb surrounding radiation and matter. Remove mass energy from a black hole through Hawking emission. The black hole becomes hotter. The reason lies in the relationship between mass and horizon size. A smaller black hole has a smaller horizon. The characteristic surface gravity is larger. Its Hawking temperature rises. The evaporation becomes increasingly rapid near the final stages. For an astrophysical black hole, however, reaching those final stages would take an extraordinarily long time. A black hole with roughly the mass of the Sun would have an evaporation time vastly longer than the current age of the universe. Supermassive black holes take even longer. What happens in the final instant is uncertain. As the black hole shrinks toward microscopic scales, its temperature becomes enormous. Quantum gravity effects should become important. Hawking's calculation treats quantum fields on a classical curved spacetime. That approximation works well when the black hole is large compared with quantum gravity scales. Near the end, the approximation breaks down. We do not know with certainty whether the black hole disappears completely, leaves behind a tiny remnant, produces a final energetic burst, or behaves in some other way predicted by a future complete theory. Hawking radiation changes the problem. If the black hole eventually evaporates completely, what happens to the information? The radiation in Hawking's original semisolical calculation appears thermal. Thermal radiation seems to depend mainly on the black hole's temperature, not on the detailed quantum state of the matter that formed the black hole. If the black hole disappears and only perfectly thermal radiation remains, the original information appears lost. That would conflict with the ordinary rules of quantum mechanics. This is the information paradox. General relativity seems to allow information to fall beyond the horizon. Quantum mechanics says information should be preserved. Hawking evaporation seems to remove the black hole. Where does the information go? For decades, this question has driven research across gravity, quantum theory, string theory, and information science. Several possibilities have been considered. Perhaps information truly is destroyed. Then quantum mechanics would need to be modified. Perhaps information escapes somehow through subtle correlations within the Hawking radiation. Then the radiation is not perfectly featureless. Perhaps information remains in a stable remnant after evaporation. Perhaps black hole interiors and exteriors are related through a deeper holographic description. The Page curve describes how the entanglement entropy of Hawking radiation should evolve if black hole evaporation preserves information. Early in evaporation, the radiation becomes increasingly entangled with what remains inside the black hole. The entropy of the radiation rises. But if the total evolution is unitary, meaning information is preserved, this entropy cannot rise forever. At a characteristic time known as the Page time, the behavior should change. Later radiation must begin carrying enough correlations that the entropy eventually decreases. When the black hole is gone, the complete radiation state can be pure again. This produces a curve that rises and then falls. Hawking's original calculation seemed instead to suggest a continuously increasing entropy for the radiation if the information remained hidden behind the horizon. The difference between these predictions became central. Hawking radiation can be described through entangled pairs of field modes associated with the horizon. In the simplest semitological picture, an outgoing Hawking quantum is entangled with a partner mode inside. As more radiation leaves, the external radiation becomes more entangled with the remaining black hole. But after the page time, if information is to escape, new outgoing radiation must also become correlated with earlier radiation. Quantum entanglement follows strict rules. One system cannot be maximally entangled with two independent systems in the same way. This tension helped lead to the firewall paradox. The firewall argument suggests that some assumptions we would like to preserve cannot all remain true simultaneously. Very roughly, we may want ordinary quantum mechanics, a smooth horizon for an infalling observer. From the outside, information may be associated with degrees of freedom near the horizon and eventually be returned in radiation. From the infalling perspective, the observer crosses normally. The two descriptions may be complementary, rather than simultaneously available in one ordinary local picture. This idea attempts to preserve both quantum mechanics and a smooth horizon, but it raises difficult questions about locality and what spacetime means at a fundamental level. String theory provides another line of thought. In string theory, black hole entropy can sometimes be counted by identifying underlying microscopic configurations. For certain highly symmetric black holes, researchers have reproduced the Bekenstein-Hawking entropy by counting quantum microstates. This was an important success. It suggests that black hole entropy really does represent microscopic quantum states. The classical black hole may be a coarse-grained description of many more detailed underlying possibilities. Some string theory approaches propose that the classical smooth interior is replaced or modified by complicated quantum structures, known in some models as fuzzballs. These ideas remain theoretical, but they illustrate a broader theme. The simple black hole geometry may emerge from deeper microscopic physics. Just as temperature emerges from the motion of molecules, spacetime geometry itself may emerge from quantum degrees of freedom we do not yet fully understand. This possibility connects black holes to another idea. Entanglement and geometry may be deeply related. In some theoretical models, especially those involving holography, the pattern of quantum entanglement in a lower dimensional theory can correspond to the geometry of a higher dimensional gravitational spacetime. This is part of why black holes have become central to attempts to understand quantum gravity. They are not only extreme astronomical objects, they may reveal how spacetime itself is built. One of the most important examples is the AD-S-CFT correspondence. The name stands for anti-de Sitter space and conformal field theory. The technical details are far beyond what we need here, but the broad idea is that a gravitational theory in one kind of spacetime can be equivalent to a quantum theory without gravity living on its boundary. A black hole in the gravitational description corresponds to a thermal quantum state in the boundary theory. Because the boundary theory obeys ordinary quantum mechanics, information is preserved there. This gives strong evidence, at least in these theoretical settings, that black hole evaporation should not fundamentally destroy information. As mass decreases, the horizon shrinks. The entropy decreases, but the emitted radiation carries entropy outward. The generalized second law of thermodynamics says that the sum of ordinary entropy outside the black hole plus the black hole's horizon entropy should not decrease. If the black hole loses area, the outgoing radiation compensates. This extended law treats black hole entropy as genuine thermodynamic entropy. The idea that a geometric area must be included in thermodynamic bookkeeping is extraordinary. A horizon behaves like part of the universe's entropy budget. This is one of the clearest signs that gravity and information are connected. Sometimes it emerges because an observer cannot access part of the quantum state. This is a subtle idea. Suppose the full quantum state contains correlations across a horizon. If an observer cannot access the region beyond that horizon, the remaining accessible state may look thermal. The loss of access creates entropy. This viewpoint helps connect horizon entropy with information. The horizon divides what an observer can and cannot see. The inaccessible degrees of freedom contribute to the thermodynamic description. Black hole entropy may therefore be connected not only to matter inside, but to the structure of quantum fields across the horizon. Different approaches emphasize different microscopic interpretations, but the recurring theme is information hidden by horizons. Now imagine a very small hypothetical black hole. Because smaller black holes are hotter, such an object could emit strongly. If the mass were small enough, the Hawking temperature could become extremely high. The evaporation time could become short. This leads to the idea of primordial black holes. Primordial black holes are hypothetical black holes that might have formed in the early universe from unusually dense regions rather than from collapsing stars. They could, in principle, have a wide range of masses. Very low-mass primordial black holes would have evaporated by now. Black holes with certain masses might be approaching their final stages today. Searches for radiation from such evaporation provide constraints on how many primordial black holes can exist. Larger primordial black holes could survive. They have been considered as possible contributors to dark matter. Whether they make up a significant fraction of dark matter depends on mass range and observational limits. The possibility remains under investigation. The importance here is that Hawking evaporation is not merely a far future curiosity. If small primordial black holes exist, evaporation could potentially have observable consequences. No confirmed detection of Hawking radiation from an astrophysical black hole has yet provided a direct experimental observation of the effect. The temperature of known large black holes is simply too low. The surrounding universe is much louder. Gravity can produce thermodynamic behavior, unlike ordinary laboratory materials. Even clusters of stars can heat up in certain senses when they lose energy. Gravity reverses some familiar intuitions because bound systems behave differently. Black holes represent the deepest version of this behavior. The thermodynamic laws of black holes can be written in forms resembling the ordinary laws of thermodynamics. There is a black hole equivalent of the first law. A change in mass relates to changes in horizon area, spin, and charge. There is a quantity called surface gravity that plays a role analogous to temperature. For a stationary black hole, surface gravity is constant across the horizon under appropriate conditions. This resembles the zeroth law of thermodynamics, which says systems in thermal equilibrium have uniform temperature. The horizon area behaves like entropy, and the area theorem resembles the second law. Once Hawking radiation is included, the analogy becomes physical. Surface gravity is proportional to temperature. Area is proportional to entropy. The laws were pointing toward quantum physics before the radiation was even discovered. This is a beautiful example of mathematical structure predicting deeper meaning. Physicists first noticed a resemblance. Entropy appears. But this simple picture is still incomplete because black hole entropy has an exact universal formula. It depends on geometry and fundamental constants. It is not merely subjective ignorance. It behaves as a physical quantity. That suggests the horizon itself carries or represents microscopic degrees of freedom. Perhaps one bit of information corresponds roughly to a certain number of Planck scale areas. This idea led to the observation that there seems to be a maximum amount of information that can be stored within a region before gravitational collapse occurs. Try to pack more and more energy and information into a fixed region. Eventually, enough energy becomes concentrated to form a black hole. The resulting black hole's entropy provides an upper bound. This is another path toward holographic thinking. The maximum information content of a region appears to scale with boundary area, not volume. The universe may be storing information differently from how ordinary intuition expects. This does not mean our three-dimensional world is literally a projected picture in the simple everyday sense of a hologram. The term holographic principle refers to a mathematical equivalence between descriptions with different dimensionalities. The underlying idea is more subtle. A gravitational region may be fully described by degrees of freedom living on a boundary. Black hole entropy provided the original clue. The information paradox also touches the meaning of locality. Locality means that physical influences act through nearby regions of spacetime. Ordinary field theories are local. A disturbance here affects neighboring regions, then propagates outward at finite speed. Black holes challenge this because information apparently stored inside may need to appear in radiation outside without an ordinary signal crossing outward through the horizon. If information escapes, perhaps the fundamental theory is not local in the simple spacetime sense, or perhaps spacetime itself is an emergent concept, and locality only appears approximately at large scales. These ideas sound radical, but they arise from trying to preserve well-tested principles. Quantum mechanics. The black hole may be one of the greatest scramblers in nature. A scrambler takes localized information and spreads it across many degrees of freedom. After scrambling, the information is still there, but no small part of the system contains it clearly. Black holes are believed to scramble information extremely rapidly. This has led to the concept of fast scrambling. The black hole's horizon may distribute information across its microscopic degrees of freedom faster than many ordinary physical systems. This connects black holes to quantum information theory. Researchers study them using concepts from computation, entanglement. In the next part, we will move gently through gravitational time dilation, redshift, light cones, proper time, the interior geometry of a black hole, what different observers can and cannot see, and why relativity allows two people to tell very different stories about the same fall without either story being wrong. Time near a black hole does not behave the way it does in everyday life. This is one of the ideas that makes black holes feel almost impossible to understand. We are used to thinking of time as something universal. 1 second passes here, 1 second passes somewhere else, and we imagine those seconds belonging to the same invisible cosmic clock. Relativity changes that picture. There is no single universal clock shared by the entire universe. Different observers can measure different amounts of elapsed time between events. Their clocks can disagree, and both clocks can still be correct. Near a black hole, this becomes impossible to ignore. The stronger the gravitational field, the more strongly clocks can differ when compared with clocks farther away. This is called gravitational time dilation. The phrase time dilation can sound as though time itself is stretching like rubber. A calmer way to think about it is to imagine two perfectly accurate clocks following different paths through space-time. One remains far from the black hole. The other moves much closer. Later, if the clocks can somehow be compared, they may show different amounts of elapsed time. Neither clock malfunctioned. Each correctly measured the time along its own path. Relativity calls this locally measured time, proper time. Proper time is the time measured by a clock traveling with an observer. Your wristwatch measures your proper time. If you fall toward a black hole, your own watch does not suddenly begin behaving strangely. Every second still feels normal. Your heartbeat continues normally. Your thoughts continue normally. A flashlight beside you behaves normally. A laboratory carried with you continues performing ordinary local experiments. The strange effect appears when your clock is compared with a clock following a different path through space-time. Suppose one observer remains far from a black hole. Another observer somehow stays near it. After a period, the nearby observer returns. The nearby observer may have aged less. This is not merely a visual effect. It is a genuine difference in elapsed proper time. Gravity changes the geometry through which both observers travel. Their paths contain different amounts of time. This idea appears even around Earth. A clock at sea level and a clock on a high mountain do not tick at exactly the same rate relative to one another. The difference is tiny, but modern atomic clocks can measure it. Clocks higher above Earth, where gravity is slightly weaker, generally tick faster relative to clocks lower in the gravitational field. Satellite navigation systems must account for relativistic timing effects. Without those corrections, positioning errors would quickly accumulate. So gravitational time dilation is not something that belongs only to black holes. Black holes simply push the effect to an extreme. Imagine slowly lowering a clock toward a non-rotating black hole, while another clock remains far away. As the first clock approaches the event horizon, the difference between the two becomes larger. The problem lies in the coordinate system. Something similar happens at the event horizon in the traditional Schwarzschild coordinates used for a non-rotating black hole. In these coordinates, the time coordinate behaves strangely at the horizon. An infalling object appears to take infinitely long to reach it. This once contributed to confusion about whether black holes could physically form, but other coordinate systems describe the horizon smoothly. An observer falling inward crosses it in finite proper time. There is no physical infinity at the horizon itself for a sufficiently large black hole. The mathematical problem was partly a coordinate problem. This distinction is important. A light cone is a diagram showing the directions that light can travel from a particular event. Because nothing with mass can move faster than light, all ordinary future paths must remain inside the future light cone. In flat spacetime, a light cone points upward in a spacetime diagram. One side represents light traveling left, the other represents light traveling right. A massive object follows a slower path somewhere between them. Near a black hole, the light cones tilt, As an observer moves closer to the horizon, the future light cones lean more strongly inward. At the horizon, the outward edge aligns with the horizon itself. Inside, the entire future light cone points inward. This means every physically allowed future path leads toward the black hole's interior. A rocket engine can change where inside the light cone the spacecraft travels. It cannot rotate the light cone itself enough to create an outward escape path. Even an infinitely powerful conventional engine cannot make a massive spacecraft move outside the local speed of light limit. The problem is no longer simply insufficient thrust. The geometry has removed outward future destinations. This is why the escape velocity explanation of a black hole is useful but incomplete. Saying the escape velocity exceeds the speed of light sounds as though a faster rocket could escape if only faster than light travel were allowed. The geometry simply reaches a point where outward escape disappears. For a large black hole, the curvature measured over a small laboratory may still be gentle. The horizon can be locally ordinary while globally decisive. Now consider what the falling observer sees while looking back toward the outside universe. A common popular claim says that someone falling into a black hole would watch the entire future history of the universe occur before crossing the horizon. This is not generally correct. The observer does see unusual distortions. Incoming light can be blue-shifted or red-shifted depending on motion and geometry. The outside universe may appear compressed into an increasingly distorted region of the sky. But the falling observer does not normally receive an infinite amount of future history before crossing a regular event horizon. Only a finite amount of external proper time can send signals that reach the observer before the observer reaches certain interior regions. The exact appearance depends on the trajectory and type of black hole. This distinction matters because gravitational time dilation is often exaggerated into a claim that one can simply hover near the horizon and watch eternity pass. Hovering is itself difficult. To remain at a fixed radius outside a non-rotating black hole, a spacecraft must continuously accelerate. Closer to the horizon, the required acceleration increases. At the horizon itself, remaining stationary would require infinite acceleration in the idealized classical model. No physical observer can hover exactly on the event horizon. A freely falling observer experiences a very different path, so statements about time near a black hole must specify which observer is being discussed. Different coordinate choices can assign different values. Spatial slices depend on how space-time is divided into space and time. This is why statements such as the singularity is exactly this many kilometers below the horizon can require careful interpretation. The horizon radius is meaningful in particular geometric senses, but the interior is not an ordinary spherical room where one can measure a static radial distance down to the center. The space-time is dynamic from the viewpoint of an infalling observer. Once inside, the singularity lies in the observer's future, not simply at another place. This is where the phrase space and time exchange roles often appears. It is a rough explanation of what happens inside a simple Schwarzschild black hole. A larger black hole generally gives an infalling traveler more proper time between crossing the horizon and reaching the classical singularity. For a stellar mass black hole, this can be very short. For a supermassive black hole, it may be longer. The key point is that the time remains finite in the classical model. Crossing the horizon does not place the traveler into an eternal interior. The singularity lies ahead. This creates another misconception. Some illustrations show a black hole as an infinitely long funnel. The funnel picture is useful for visualizing curved space in a simplified way, but it should not be interpreted literally. The black hole can be approached from any side. The horizon is spherical in the non-rotating case. Every inward direction leads toward the center. The funnel only represents curvature using an extra visual dimension. It cannot show the true causal structure. A better conceptual tool is the space-time diagram. One particularly useful diagram is called a Penrose diagram. A Penrose diagram compresses infinite distances and times into a finite shape while preserving the causal relationships of light rays. The mathematical construction is more advanced. A real star did not begin its history with an eternal event horizon extending infinitely into the past. The horizon formed during collapse. The space-time before formation looked very different. This makes the word eternal black hole a technical idealization. It is useful because its symmetry makes equations easier to study. But astrophysical black holes have histories. Another source of confusion concerns what the outside observer sees after someone crosses. Suppose an astronaut falls into a black hole. Can the distant observer still say the astronaut exists? Relativity does not give a simple universal present shared by both observers. The question what exists right now becomes coordinate-dependent over large space-time separations. The distant observer continues receiving old light from the astronaut. The signals become increasingly redshifted. Eventually, no useful new information arrives. From the infalling astronaut's perspective, the crossing and later events happen normally along their world line. There is no need to choose one observer's present as universally real. Relativity replaces universal simultaneity with causal relationships. Which events can influence which others? Can a light signal connect them? Can the observer receive information? These questions are more physically meaningful than asking what is happening everywhere at one cosmic instant. This is one of the deepest philosophical consequences of relativity. The universe is not naturally divided into a sequence of universal snapshots. Different observers divide space-time into space and time differently. Near a black hole, those differences become especially dramatic. The event horizon itself depends on the global causal structure. To identify it perfectly, one must know whether future-directed light can eventually reach infinity. This can create strange thought experiments. Imagine a star begins collapsing, but somehow reverses before a black hole fully forms. A temporary region may resemble a horizon locally. A map of the whole river can identify a watershed boundary even if someone standing at one point does not yet know where the water eventually flows. The global definition uses the entire map. The horizon is similar. Another subtle issue concerns the speed of infalling objects. A distant observer using certain coordinates may calculate the infalling object as slowing near the horizon. A local observer who is freely falling nearby measures something different. A hypothetical observer hovering just outside the horizon may measure the infalling object moving close to the speed of light, but the hovering observer requires greater and greater acceleration as the horizon is approached. In a stationary spacetime, one can define conserved quantities associated with symmetries. The photon's local energy differs between observers at different gravitational potentials. The change is not best pictured as the photon spending energy like fuel while climbing. Rather, different observers decompose the spacetime and measure the photon differently. The same principle appears when light falls inward. An observer deeper in the gravitational field may measure the photon as blue-shifted. Its frequency is higher. Gravitational redshift and blueshift are observer-dependent comparisons. This does not violate energy conservation. Energy in curved spacetime must be defined with care. Physics becomes clearer when those questions are asked explicitly. Now imagine a clock orbiting a black hole. Its time is affected by both gravity and speed. A stable orbit near a black hole requires high orbital velocity. Special relativistic time dilation slows the orbiting clock relative to a distant observer. Gravitational time dilation also contributes. The closer orbit therefore experiences less proper time than a distant stationary clock. This is analogous to satellites around Earth, where both gravitational and velocity effects matter. Around a black hole, both become much stronger. For a non-rotating black hole, stable circular orbits end at the ISCO. Inside that radius, no stable circular orbit exists. A spacecraft could still follow temporary trajectories, but remaining in a stable orbit is no longer possible. This places limits on how much gravitational time dilation can be obtained through simple stable orbiting. One cannot simply choose a radius arbitrarily close to the horizon and remain there in a free circular orbit. For a rotating black hole, the ISCO can lie much closer to the horizon for co-rotating motion. This can produce stronger relativistic effects. Spin therefore influences possible time dilation scenarios, as well as accretion. A rapidly rotating black hole changes orbital structure dramatically. In the extreme mathematical limit, certain co-rotating orbits approach very close to the horizon. Real black holes are not expected to reach the exact ideal extremal limit through ordinary astrophysical processes. Accretion and radiation place practical restrictions, but high spin can still create substantial differences. Now ask whether the black hole itself experiences time. This question is tricky because a black hole is not one material object with one clock. A stationary exterior spacetime can be described with a time coordinate. The horizon has its own geometric structure. An infalling observer has proper time. A distant observer has another. There is no single black hole clock sitting at the center. Suppose the black hole is non-rotating. After crossing the horizon, the traveler sends a beam of light outward. The light still moves locally outward relative to the traveler in an immediate small region, but globally, its radial coordinate continues decreasing. This statement can sound contradictory because local outward and global inward are being mixed. In curved spacetime, local directions do not always correspond to simple global coordinate changes. Imagine walking north on Earth. Near your location, north is perfectly well defined. Continue long enough, and eventually all northward paths converge at the pole. Global geometry changes how local directions fit together. A geodesic is the natural free-fall path through spacetime. In flat spacetime, parallel geodesics remain parallel. In curved spacetime, they can converge or diverge. Tidal gravity is a manifestation of this. Near a black hole, two freely falling particles initially separated slightly may experience changing separation. One closer to the center accelerates differently from the other. Their relative motion reveals curvature even though each individually feels weightless. This is one of Einstein's deepest insights. Gravity can be removed locally by free fall, but curvature cannot be removed over an extended region. The tidal effect remains. A black hole is not defined merely by a strong gravitational acceleration that one could cancel by falling. It is defined by global geometry and curvature. This also explains why saying gravity becomes infinite at the event horizon is wrong. For a sufficiently massive black hole, the local curvature at the horizon can be quite moderate. What becomes special is the causal boundary. The infinite quantities sometimes appearing in old descriptions come from coordinates or from the acceleration required to hover. The traveler in freefall does not measure infinite gravity there. The strongest classical curvature occurs toward the singularity. This distinction is crucial. Something called mass inflation can occur. Small amounts of incoming and outgoing radiation can become enormously blue-shifted near the inner horizon. The effective energy density can grow dramatically. This suggests that the neat eternal Kerr interior may not survive in a realistic black hole. The actual interior could become much more violent. Quantum effects may alter it further, so diagrams showing a rotating black hole as a safe tunnel through a ring should be treated cautiously. The exact classical solution is mathematically fascinating. The astrophysical interior is likely less tidy. No observation from inside can return to tell us. Newtonian mechanics still works for ordinary speeds, even though relativity extends it. General relativity may work extremely well outside and around black holes, while requiring quantum modification at the deepest interior. Physics builds layers. New theories often preserve old successful predictions where those predictions were tested. A future quantum gravity theory should reproduce general relativity for large, low-curvature black holes, then alter the description only where quantum effects become unavoidable. Time inside a black hole may therefore be one of the places where our current language is temporary. The classical picture says future paths terminate at a singularity. The quantum picture is unknown. Perhaps the singularity is replaced by a quantum region. Regions may exist from which light emitted now will never reach us, not because a wall blocks it, because expansion changes the global spacetime structure. Accelerating observers can have Rindler horizons. Again, there are regions they can never receive signals from. Horizons are therefore not unique to black holes. They arise whenever spacetime or observer motion divides accessible from inaccessible events. Black holes provide the most dramatic gravitational example. This connection also helps explain why horizons have thermodynamic properties. If an observer lacks access to part of a quantum field because of a horizon, the remaining accessible state can appear thermal. Observers far away detect gravitational waves delayed by the finite speed of propagation. Even here, there is no universal present connecting the merger and the detector. The wave travels across spacetime. The event happens. Then much later, by our local clocks, its influence arrives. Astronomy always looks into the past, because light and gravitational waves require time to travel. When we observe a black hole merger billions of light years away, we see an event that happened billions of years in the source's history. The universe is already a time machine in this ordinary observational sense. The farther away we look, the earlier we see. Black holes add gravitational distortion to this already relativistic universe. Near a black hole, the difference becomes dramatic. A distant observer sees light from a falling object become increasingly redshifted and delayed. The object appears to slow and fade near the horizon. The falling observer does not experience their own time stopping. They cross the horizon in finite proper time. The apparent infinite delay belongs to a particular distant coordinate description. Different coordinates can describe horizon crossing smoothly. The event horizon is not a physical wall, it is a causal boundary. Light cones tilt inward as the horizon is approached. Inside, every future-directed path leads deeper toward the interior. Even light aimed outward cannot reach the distant universe. The local speed of light remains unchanged. The global geometry determines where the light can go. Inside a simple non-rotating black hole, the singularity lies in the future of every infalling observer. This is why saying space and time exchange roles can be useful, though incomplete. Moving inward becomes unavoidable in a way that resembles moving toward the future. A traveler cannot hover or turn around after crossing. The remaining proper time is finite. For large black holes, horizon crossing may be locally gentle. In the next part, we will move gently into what lies deeper in the black hole interior. What physicists actually mean by a singularity. Why infinite density may signal the failure of a theory rather than a literal physical point. How rotating black holes change the classical picture. What wormholes and white holes really are, and where established physics ends and speculation begins. The deepest part of a black hole is also the part we understand least directly. Outside the horizon, astronomers can watch stars orbit. They can measure hot gas. They can detect X-rays. They can observe gravitational waves. They can study the shape of black hole shadows. But once something moves beyond the event horizon, no ordinary signal from that region can return to us. The interior is hidden. So when physicists describe what happens there, they rely on theory. And the main theory is general relativity. General relativity has passed many difficult tests. It accurately describes planetary motion, gravitational lensing, time dilation, binary pulsars, gravitational waves, and much of black hole behavior outside the horizon. So it is natural to use the same equations to explore the interior. But something strange happens when those equations are followed far enough. They predict a singularity. The word singularity is often used as though it describes a tiny object sitting at the center of a black hole. Perhaps an infinitely dense dot, perhaps a mysterious ball, perhaps a place where matter has been compressed into zero volume. These pictures are common, but they can be misleading. A singularity in general relativity is more carefully understood as a place where the classical description of spacetime becomes incomplete. Some quantities may diverge. Paths through spacetime may come to an end after finite proper time. The equations can no longer continue the ordinary geometric description. This does not automatically tell us what nature physically contains there. It tells us that the theory has reached a limit. Imagine using a map that works perfectly across an entire country. Roads, rivers, mountains, distances, everything is accurate. Then, at one particular region, the map simply stops. Lines become compressed. In the simplest black hole, it lies in the future of anyone who crosses the horizon. This is why every infalling observer reaches it, not because the singularity is pulling them through an ordinary room, because the singularity lies along their future path. Once again, the analogy to tomorrow can help. You do not need a force dragging you toward tomorrow. Moving into the future is built into your path through spacetime. Inside a simple black hole, moving toward the singularity becomes similarly unavoidable. This is also why the phrase center of the black hole can be misleading. Outside the black hole, future-directed light can move inward or outward. At the horizon, the outward light ray stays on the boundary. Inside, even the most outward-directed light moves toward the singularity. The singularity appears not as a small dot at the bottom. It appears as a future boundary stretching across the interior. Every future path eventually reaches it. This picture is closer to the relativistic meaning. Now ask what happens to matter physically as it approaches the singularity. Classically, tidal forces grow. The difference in gravity between nearby parts of an object becomes extreme, far smaller than an atomic nucleus. At distances approaching the Planck scale, many physicists expect quantum gravity effects to become unavoidable. There is also a Planck time, a Planck mass, and a Planck energy. These quantities combine the fundamental constants of gravity, quantum mechanics, and relativity. They mark a region where our usual separation between spacetime geometry and quantum fields may fail. A black hole singularity pushes the classical theory toward precisely this regime. This is why singularities are not merely inconvenient infinities. They are clues. Perhaps at tiny scales, space-time has a more fundamental quantum structure. If so, the singularity may be what happens when we mistakenly continue the smooth approximation beyond the scale where it is valid. This is only an analogy. We do not know whether space-time is literally made from discrete pieces, but many approaches to quantum gravity suggest that smooth geometry is not the deepest description. The black hole interior may reveal whatever lies underneath. Now consider the theorem behind the singularity. In the 20th century, Roger Penrose and later Stephen Hawking showed that singularities are not merely artifacts of perfectly symmetric calculations. Under broad physical conditions, gravitational collapse leads to geodesic incompleteness. This means some paths through spacetime cannot be extended indefinitely. Tiny perturbations matter. This becomes especially important near something called the inner horizon. A rotating Kerr black hole contains an outer event horizon and an inner horizon in the ideal mathematical solution. The inner horizon is also called a Cauchy horizon. The name comes from predictability. In ordinary classical physics, if we know the complete state of a system on one suitable surface, the equations allow us to predict what happens later. A Cauchy horizon marks a boundary beyond which that ordinary predictive structure becomes problematic. Beyond it, the mathematical extension is no longer uniquely determined by the earlier data in the same way. This sounds very abstract, but physically, the inner horizon is also expected to be unstable. Imagine small amounts of radiation falling inward. Some radiation may also be scattered within the black hole. Near the inner horizon, these streams can become enormously blue-shifted relative to one another. Their effective energy grows. The curvature can increase dramatically. This phenomenon is called mass inflation. The name does not mean a new ordinary object suddenly gains physical rest mass. It refers to certain internal mass parameters and curvature quantities growing without bound in the classical analysis. The result suggests that the smooth inner horizon of an ideal Kerr black hole is not realistic. A real rotating black hole may develop a highly singular region there. Ordinary matter tends to make gravity focus paths inward. Keeping a wormhole open appears to require unusual stress energy, often described as exotic matter. This does not mean antimatter. Antimatter has positive mass energy and behaves gravitationally, much like ordinary matter. The exotic requirement usually involves negative energy density in certain frames or violation of classical energy conditions. Quantum physics can produce small negative energy effects in limited situations. The Casimir effect is a commonly discussed example, but whether enough controlled negative energy could support a macroscopic traversable wormhole is unknown. No such wormhole has been observed. Detecting them separately may require much better angular resolution and sensitivity, perhaps additional Earth stations, perhaps observing at shorter wavelengths, perhaps radio telescopes in space. A space antenna could create baselines larger than Earth. Not every photon we see was emitted at the same source time. Different paths have different lengths. Some rays travel almost directly, others loop around the black hole. So different portions of one image may represent the plasma at slightly different moments. The black hole image is therefore not one perfectly simultaneous snapshot in an ordinary sense. Strong lensing creates time delays. Around M87's giant black hole, those delays can be substantial. Around smaller black holes, shorter. If the plasma changes during the delay, repeated images of the same region may show different stages of its evolution. This intertwines geometry and time. The image is a map not only of space, but of light travel histories. This is a common idea in gravitational lensing more broadly. A distant quasar lensed by a foreground galaxy can appear as several separate images. If the quasar brightens, each image may brighten at a different time because the light paths have different lengths and gravitational delays. Astronomers can measure these delays. Near a black hole, the same principle operates at much smaller scales and much stronger curvature. Photon paths differ dramatically. Now ask whether the black hole blocks the stars behind it. A realistic black hole does not need a glowing accretion disk to reveal itself. Against a background of stars, its shadow and lensing could still be visible. The darkness would be outlined by warped starlight. The accretion disk simply makes the effect much brighter and easier to detect astronomically. Now imagine approaching the black hole yourself. The visual appearance becomes even stranger. Far away, The black hole occupies a small part of the sky. As you approach, the dark region grows. Background stars are lensed around it. Multiple images appear. Why spin? Because the ISO changes with spin. If matter orbits in the same direction as a rapidly spinning black hole, the stable disk can extend closer inward. That deeper region produces stronger gravitational redshift, so the shape of the spectrum contains information about the geometry. Horizon-scale radio imaging and X-ray spectroscopy approach the same object from different directions. One maps brightness, the other maps energy distributions. Both use light distorted by spacetime. Now consider another technique called reverberation mapping. Longer delay, larger separation. Around supermassive black holes, these delays can help map the inner accretion geometry. This illustrates a broader principle. Astronomers rarely resolve small systems directly. Sometimes they infer size through timing. If a source varies rapidly, it must be compact. If reflected light arrives after a delay, the delay constrains distance. If gravitational waves change phase, the phase reveals orbit. Black hole science uses time almost as often as images. An accretion disk around the small black hole can teach us about the giant one. The giant can be imaged. The small one can evolve rapidly. Together they provide complementary experiments. Another important observational method involves the motion of stars near a supermassive black hole. We already discussed Sagittarius, a star. The orbits reveal the central mass, but the details can also test relativity. An elliptical orbit in Newtonian gravity would repeat with a fixed orientation in an ideal two-body system. Relativity introduces additional precession. The orbit slowly rotates. The point of closest approach shifts. This is similar to the famous relativistic precession of Mercury around the Sun. Near the galactic center, the effect is much stronger. By observing stars passing close to Sagittarius, a star, astronomers can test whether their motion follows relativistic predictions. The stars become natural probes. Their light also experiences gravitational redshift as they pass deep into the potential. Their enormous orbital velocities create Doppler shifts. Careful spectroscopy separates these effects. Again, black hole evidence is not one image. Massive compact objects described remarkably well by black hole solutions of general relativity. This convergence is more powerful than any iconic photograph. Now ask whether the Event Horizon Telescope proves an event horizon exists. The answer requires precision. The observations strongly support an extremely compact object with a shadow size consistent with a general relativistic black hole. Combined with other measurements, the case for black holes is very strong. But imaging alone does not literally watch an object cross the horizon and fail to return. Alternative hypothetical compact objects could sometimes be engineered to mimic aspects of the shadow. That is why researchers compare models carefully. If such an alternative has a surface, incoming matter may heat the surface and create extra radiation. If it reflects light, the image may change. If its space-time differs, photon trajectories may change. Observations constrain these alternatives. As measurements improve, hiding differences becomes harder. Science rarely proves an interpretation through one observation. Instead, alternatives are progressively constrained. Black holes survive because many independent tests agree. This is the same reason we are confident stars contain nuclear fusion, even though no probe has visited the solar core. The theory explains many observations at once: gravitational waves, neutrinos, cosmic rays. Different physical signals provide different perspectives. Black holes are especially important in this multi-messenger universe because they can participate in nearly every category except sending ordinary signals from behind the horizon. A black hole swallowing a neutron star may produce gravitational waves. Perhaps light, if matter remains outside long enough. Perhaps heavy elements in ejecta. A supermassive black hole can produce electromagnetic jets, and perhaps high-energy neutrinos through surrounding particle acceleration. The horizon remains silent. A photon orbiting the black hole is still locally moving at light speed. The geometry curves its trajectory. No photon is hovering motionlessly. At the event horizon of a non-rotating black hole, an outgoing light ray can remain at the same Schwarzschild radial coordinate in one mathematical description, but locally, the photon still moves at c. Coordinate language and local measurement must not be mixed. This distinction is the same one we encountered with falling objects freezing at the horizon. Coordinates can behave strangely. Local physics remains regular. Or if mass is known independently, the shadow can test the expected geometry. For Sagittarius A star, the mass and distance are already constrained through stellar orbits. This makes the shadow size a strong consistency test. For M87, stellar and gas dynamics provide independent mass estimates. Again, imaging can compare. Independent methods do not need to be identical. Their uncertainties can differ, but broad agreement strengthens confidence. Now think about measurement uncertainty. A published image looks crisp enough to suggest certainty at every pixel. The Event Horizon Telescope image is the visible summary of an enormous data analysis process. Another interesting quantity is closure phase. In interferometry, atmospheric disturbances can corrupt the absolute phase measured at individual telescopes. But certain combinations of phases around a triangle of 3 observatories cancel some telescope-specific errors. These combinations are called closure phases. They carry information about asymmetry in the source. A perfectly symmetric source produces one kind of behavior. A crescent-like structure produces another. Closure quantities are therefore powerful because they remain robust even when individual atmospheric phases are unstable. Now consider what a future black hole image might reveal. Perhaps the spin orientation. Perhaps the precise photon ring geometry. Perhaps time-variable plasma orbiting close to the ISCO. Perhaps the footprint of a jet launched near the horizon. Perhaps magnetic field lines changing. Perhaps signatures of frame dragging. If repeated high-resolution observations can track features moving around the black hole, we may watch strong gravity evolve in real time. The rotation of space-time could leave observable patterns. Material moving with the spin behaves differently from matter moving against it. How does a jet remain narrow from the central region all the way into intergalactic space? Magnetic fields are likely central. A rapidly spinning black hole may contribute rotational energy. The surrounding disk supplies plasma. The jet accelerates, then gradually collimates. Different wavelengths probe different distances from the black hole. Radio telescopes with lower resolution see large-scale jet structure. Higher frequency VLBI sees closer in. The Event Horizon Telescope reaches the innermost scales. Combine them, and astronomers can trace the jet from the horizon outward. This connects the smallest and largest structures. A black hole only billions of kilometers across can influence plasma over distances of thousands of light years. Again, scale becomes astonishing. The horizon is tiny compared with the galaxy. The jet is huge. The bridge between them is magnetic and relativistic physics. This is why understanding accretion is essential to galaxy evolution. The black hole's gravity does not directly dominate an entire galaxy. Even if located relatively nearby in the Milky Way, its angular size would be extraordinarily tiny, much smaller than current horizon-scale resolution. So direct imaging is unlikely with present technology. But gravitational microlensing may reveal isolated stellar black holes. X-ray binaries reveal accreting ones. Gravitational waves reveal merging ones. Every mass range has its observational method. Intermediate mass black holes remain particularly interesting because they sit between. A nearby enough intermediate mass black hole might someday become an unusual imaging target. But identifying such objects securely remains challenging. The accretion brightness may be much more asymmetric than the shadow geometry itself. One side shines because of Doppler boosting. The dark central outline remains comparatively regular. Distinguishing brightness asymmetry from geometric asymmetry is essential when testing spin. The plasma can move. The geometry changes more subtly. Another effect is light polarization rotation. As polarized radiation travels through magnetized plasma, its polarization direction can rotate. This is called Faraday rotation. The amount depends on the magnetic field. What happens in the final stages of evaporation? What are the biggest unanswered questions? And after all the confusing pieces are gathered together, what should we actually remember about black holes? In the final part, we will move slowly through primordial black holes, dark matter, the distant future of black holes, evaporation over unimaginable timescales, the limits of what modern physics knows, and a gentle final recap connecting horizons, gravity, time, information, quantum theory, and the long life of the universe. Black holes may be among the strangest objects in the universe, but they are not separate from the universe. They are part of its history. They form from stars. They grow inside galaxies. They merge. They influence surrounding gas. and over timescales almost impossible to imagine, they may become some of the last large objects remaining. To understand the future of black holes, we first move backward, very far backward, toward the beginning of the universe. Most black holes we have discussed so far form through astrophysical processes. A massive star collapses. A neutron star becomes too massive. Two compact objects merge. A supermassive black hole grows through accretion and repeated mergers. But there may be another possibility. Black holes might also have formed in the early universe. These hypothetical objects are called primordial black holes. The word primordial means originating extremely early. A primordial black hole would not need to begin with a star. Instead, it could form if a region of the young universe became dense enough to collapse under its own gravity. The early universe was extremely hot, dense, and nearly uniform. Nearly. Small variations existed. Some regions contained slightly more matter and energy than others. Those tiny differences eventually grew into galaxies, clusters, and the enormous cosmic structure we observe today. But if certain regions had been much denser than average, gravity might have caused them to collapse directly. A black hole could form. Because the early universe contained conditions unlike anything that exists today, primordial black holes could potentially have formed with a wide range of masses. Some might be tiny. Some might be comparable to asteroids. Some perhaps comparable to planets. Others might be much larger. The details depend on which early universe processes produce the density fluctuations. This is one reason primordial black holes remain interesting. One reason primordial black holes receive so much attention is dark matter. Dark matter is the name given to an invisible form of matter, inferred mainly through gravitational effects. Galaxies rotate as though they contain more mass than their visible stars and gas provide. Galaxy clusters behave similarly. Gravitational lensing reveals additional mass. The large-scale structure of the universe also points toward a substantial non-luminous matter component. We call it dark because it does not appear to emit, absorb, or reflect ordinary light in the usual way. We know what dark matter does gravitationally. We do not yet know its fundamental identity. Many possibilities involve new elementary particles. The allowed contribution depends strongly on mass. Some mass ranges are tightly constrained. Others remain more open. It is possible that primordial black holes contribute some fraction of dark matter without making up all of it. Whether they contribute significantly remains an active question. No confirmed observation has established primordial black holes as the dominant dark matter component, so it is useful to separate the idea from the evidence. Primordial black holes are a plausible theoretical possibility. They are searched for. They are constrained by observations. Their cosmological importance remains uncertain. One search method is microlensing. Imagine a compact dark object passing in front of a distant star. Its gravity bends the star's light. For a period, the star appears brighter, then returns to normal. The duration of the brightening depends partly on the lens mass and motion. Surveys can monitor millions of stars. If a large population of black holes existed in a certain mass range, characteristic lensing events should occur. The number observed can constrain the population. Another method involves gravitational waves. If primordial black holes exist, some could form binaries and merge. Their masses, spins, and merger history might differ statistically from black holes produced by stars. For example, a black hole found in a mass range that is difficult for ordinary stellar evolution could raise questions. But one unusual mass is not enough. Stellar black holes can grow through mergers. Dense clusters can produce complicated populations. Faster evaporation. Very low-mass primordial black holes formed in the early universe might already have evaporated. Others with somewhat larger masses could still exist. If some were reaching their final evaporation stages today, they might produce energetic radiation. Searches look for such signals. No confirmed detection has established an evaporating primordial black hole, but non-detections place limits on how common they can be. So even something we have not found can still teach us. The absence of a signal constrains the universe. Now step away from the early universe, then perhaps an extremely dilute era after black holes themselves have evaporated. These are not future dates on a calendar. They are ways of organizing unimaginably long physical timescales. During the black hole era, black holes may become among the largest remaining bound concentrations of mass. supermassive black holes will last the longest. Why? Because larger black holes are colder. Their Hawking radiation is weaker. Their evaporation time increases strongly with mass. A stellar mass black hole already survives for an astonishingly long time. You would still not approach the lifetime of the largest black holes. The final era of black holes belongs to a universe almost completely different from ours. This raises a quiet question. If no one is present to watch, does the black hole still evaporate? Physics says the process does not require an observer. Hawking radiation is not produced because someone looks. The quantum fields and space-time geometry evolve according to physical laws. The radiation travels outward whether or not any detector receives it. The universe does not need witnesses. Now think about the final evaporation stage. One modern lesson is that a black hole horizon may not divide information as simply as classical geometry suggests. Classically, there is an outside and an inside. The horizon separates them. Quantum theory introduces entanglement. The state of one region may be deeply correlated with another. In holographic descriptions, information that appears to reside in a bulk gravitational region can be encoded in degrees of freedom associated with a boundary. The idea of where information is located becomes less obvious. Perhaps asking where the information is stored assumes too classical a picture. A quantum state can be distributed, encoded, redundantly represented, or recoverable from correlations that do not correspond to one simple location. Quantum error correction provides a useful conceptual analogy. In certain quantum codes, the information describing one logical quantum state is spread across many physical components. Lose a few components, the logical information can still be reconstructed from the rest. No single component contains the whole message. Some modern approaches to holography suggest space-time itself may behave with similar informational redundancy. A region of the gravitational interior might be encoded in multiple ways in an underlying quantum theory. This is highly theoretical, but it offers a language for understanding why information might survive even when the classical interior seems inaccessible. Black holes therefore connect astrophysics to quantum computing ideas. A collapsing star leads to entropy. Entropy leads to information. Information leads to entanglement. Entanglement leads to questions about space-time. A subject that begins with gravity ends by asking what reality is made of. Quantum states. For a black hole, the underlying degrees of freedom are less obvious. String theory has successfully counted microstates for certain special black holes. Other approaches propose quantum geometry states. Entanglement across the horizon may contribute. Holographic theories provide boundary descriptions, but a complete intuitive microscopic picture for every realistic astrophysical black hole remains unfinished. This is one of the central tasks of quantum gravity. A successful theory should explain why the entropy is proportional to area, why the coefficient has exactly the observed theoretical form. Physics has encountered similar boundaries before. Before atomic theory, temperature was understood macroscopically. Before quantum mechanics, atoms themselves were mysterious. Before relativity, gravity was described without space-time curvature. The absence of a complete theory today does not mean the question cannot be answered. It means the work is unfinished. Black holes show us where to look. Another deep question is whether event horizons truly exist as exact permanent boundaries in a universe where black holes evaporate. An eternal classical black hole has a mathematically precise event horizon extending into the future, but an evaporating black hole eventually disappears. Encoded at the boundary, released gradually, the precise meaning of the horizon influences the answer. This is another example of different scales requiring different descriptions. For astronomy, the horizon acts like a robust one-way boundary. For quantum gravity theory, its microscopic nature may require refinement. Both levels can be valid within their domains. Another question concerns black hole interiors and entanglement. Could an interior emerge from the entanglement structure of exterior degrees of freedom? In holographic models, portions of bulk spacetime can be reconstructed from information in a boundary theory. The horizon then becomes especially important because it sits at the boundary between classical geometry and quantum information. This is one of the most ambitious directions in modern theoretical physics. It may turn out to be incomplete, but it shows how deeply black holes have changed our questions. The first black hole discussions asked whether gravity could become strong enough to trap light. Now physicists ask whether entanglement creates geometry. The same object pushed the subject from astronomy toward the foundations of reality. Another unresolved area is the connection between black holes and dark energy. Dark energy is the name given to whatever drives the observed accelerated expansion of the universe in the standard cosmological description. Black holes are not currently considered a simple established explanation for dark energy. Quantum gravity, wormholes, all may appear near black holes in popular discussions, but the scientific relationships differ. Black holes could contribute to dark matter if primordial populations exist. That is plausible but unconfirmed. Dark energy has a different observational role. Wormholes are mathematical possibilities without confirmed detection. Quantum gravity is expected to become important in black hole interiors. Each connection must be evaluated separately. Did the galaxy determine how much the black hole could grow? Likely both processes interacted. This is called coevolution. The black hole grows because the galaxy supplies material. The galaxy changes because black hole activity returns energy. Feedback forms a loop. This makes supermassive black holes important, even though they contain only a small fraction of a galaxy's total mass. A black hole may not gravitationally control the outer galaxy, but its accretion output can influence gas far beyond the region where its direct gravitational dominance ends. This distinction is important. The largest known black holes reflect both their growth efficiency and the histories of their host systems. In the distant future, galaxy mergers may combine some central black holes into even larger objects. Local gravitationally bound structures can continue merging even while the wider universe expands, but accelerated cosmic expansion can isolate distant groups from one another. Eventually, some regions disappear beyond each other's cosmic horizons. A black hole in one isolated future structure may never interact with black holes in another. Cosmic expansion therefore places a large-scale limit on future mergers. The universe can expand fast enough that distant regions lose causal contact. This produces another kind of horizon, a cosmological horizon. A cosmological horizon can also possess thermodynamic properties. This suggests the black hole relationship between gravity and thermodynamics is not an isolated accident. It may reflect something fundamental about spacetime. Perhaps gravitational field equations themselves have a thermodynamic interpretation. Some theoretical work explores whether Einstein's equations can be understood as equations of state, like pressure and temperature relationships in ordinary matter. If so, gravity may be an emergent macroscopic phenomena, just as fluid behavior emerges from molecules. Again, this is a deep theoretical possibility, but black hole thermodynamics is one of the clues that motivates it. Then perhaps gravity is not a fundamental force in the same sense we once assumed. Perhaps it is a large-scale behavior of deeper microscopic degrees of freedom. This would be similar to temperature. Temperature is real, but no individual molecule possesses temperature in the same way a gas does. Temperature emerges from collective behavior. Perhaps space-time curvature is similarly emergent. Black holes would then be like thermodynamic systems, revealing the microscopic nature of geometry. We do not know whether this is the final answer, but it shows why black hole entropy is more than a strange formula. It may be a window into the origin of gravity. Now return to something concrete. What would happen if Earth approached a black hole? The answer depends entirely on distance and mass. A black hole is not a universal cosmic vacuum cleaner. Far away, its gravity behaves like that of any object with the same mass. If a 10 solar mass black hole passed hundreds of light years away, its direct gravitational effect on Earth could be negligible. If it passed extremely close to the solar system, its gravity could disrupt planetary orbits. But the same would be true for an ordinary star of comparable mass passing similarly close. What makes the black hole special is its compactness. The accretion disk may be violent. Popular images often merge those ideas. Physics separates them. Another misconception is that the event horizon itself is the singularity. It is not. The event horizon is the boundary beyond which signals cannot return. The singularity lies deeper in the classical description. For a huge black hole, these regions can be separated by an enormous horizon scale. Crossing one does not mean instantly reaching the other. Another misconception says time completely stops at the horizon. It does not for the falling observer. The distant observer receives increasingly delayed signals. Proper time for the traveler continues. Another says light cannot escape because gravity slows it below the speed of light. Locally, light always travels at sea. The geometry determines that future directed paths from inside do not reach the exterior. Another says black holes are infinitely dense everywhere. They are not. The horizon itself can have moderate curvature for a supermassive hole. The classical singularity involves divergent quantities deeper inside. The radiation emerges from quantum field behavior associated with the spacetime and horizon. Nothing locally travels outward from behind the horizon into the exterior in the ordinary classical picture. Another says the Event Horizon Telescope photographed the singularity. It did not. It imaged emission around the black hole and the dark shadow created by strongly bent and captured light. The horizon lies inside the apparent shadow. These corrections are useful because they replace dramatic metaphors with clearer ideas, and strangely, the real physics often becomes more interesting than the metaphor. A black hole is not a giant vacuum cleaner. It is a causal structure. Quite the opposite. The exterior may be simple. The quantum interior is mysterious. The same object can be understood extremely well and poorly at different scales. This is another lesson worth remembering. Scientific knowledge is not all or nothing. We can understand how a black hole bends light with great precision while not knowing what replaces the singularity. We can predict gravitational wave ringdown while debating the microscopic origin of entropy. We can image a shadow while lacking a direct detection of Hawking radiation from an astrophysical black hole. Different questions have different levels of certainty. Outside, some future paths point outward. At the horizon, the boundary becomes light-like. Inside, all future directed paths lead deeper in. The event horizon became a statement about causality rather than force. Then we reached the interior. Classical relativity predicts a singularity. But the singularity is not necessarily a literal, infinitely dense object we should imagine as a tiny ball. It tells us the classical spacetime becomes incomplete. Quantum gravity should eventually replace the description. We do not yet know exactly how. Rotation complicates the interior further. Ideal Kerr solutions contain inner horizons and unusual mathematical extensions. Realistic perturbations likely make parts of that structure unstable. Wormholes remain theoretical. White holes remain unconfirmed. Science fiction portals are not established consequences of ordinary astrophysical black holes. Then we encountered thermodynamics. Black hole area behaves like entropy. The horizon contains an enormous entropy proportional to its area. Quantum theory gives the black hole a temperature. Hawking radiation appears. Small black holes are hotter. Large black holes are colder. A black hole can slowly lose mass. Then the information paradox appeared. If the black hole evaporates completely, what happens to information about everything that formed it? Quantum mechanics suggests information should be preserved. Hawking's original thermal descriptions seem to threaten that principle. Modern approaches increasingly suggest that information may survive in subtle quantum correlations. The Page curve. Primordial black holes may have formed before stars. Some could contribute to dark matter. The possibility remains unconfirmed. Astrophysical black holes will survive for immense times. Eventually, in a sufficiently cold universe, Hawking evaporation dominates. The black holes shrink, warm, radiate faster, and reach a final quantum gravity regime whose exact outcome remains unknown. The story of a black hole therefore stretches from the death of stars to the potential far future of the cosmos. If it rotates, it drags nearby geometry. Matter outside can orbit and glow. Light close to it bends strongly. Inside the horizon, signals cannot return. The deepest classical interior reaches a singularity where general relativity becomes incomplete. Quantum theory gives the horizon entropy and temperature. Black holes can eventually evaporate, and that evaporation leads to difficult questions about information and the microscopic nature of spacetime. Observations show that black holes are not merely theoretical. We know where the boundaries of current knowledge lie. The exterior geometry is tested remarkably well. The event horizon scale is increasingly observable. The singularity is hidden. Hawking radiation is strongly predicted, but extraordinarily difficult to observe directly in astrophysical black holes. The final evaporation stage remains unknown. The microscopic explanation of entropy remains incomplete. The full reconciliation of gravity and quantum mechanics remains unfinished. These are not vague gaps, they are defined questions. And defined questions can guide future science. Perhaps future gravitational wave observatories will map black hole spacetime with extraordinary precision. Perhaps future radio arrays will resolve photon rings. Perhaps we will discover intermediate mass black holes in large numbers. Perhaps primordial black holes will be found. Perhaps a direct signature of Hawking radiation will someday appear under unexpected circumstances. Perhaps quantum gravity will explain singularities. Perhaps black hole information will become a solved problem. We do not know, but every new observation narrows the possibilities. Space-time rings. Quantum effects give black holes temperature. Entropy connects horizons to information, and somewhere beyond the reach of classical theory, the deepest explanation is still waiting. There is nothing more to solve tonight. Allow the ideas to become distant. Allow the words to become quieter. The universe can continue without being understood all at once. The black holes can keep their final secrets for another night. Sleep well, and good night.